Over the last few videos, we've been working with Simpson's rule, but in the first video, I made a promise. I said we are going to derive Simpson's rule, and I want to do that in this video. I want you to have some intuition behind how you can get Simpson's rule. So what we're going to do, I've graphed out f of x up here, and we're going to apply Simpson's rule with two subintervals to approximate this definite integral right here. So let's do that. We're going to take Simpson's rule with two subintervals, and that's going to be equal to delta x over 3. So let's get delta x sorted out here first. So our full length of the interval is going to be h minus negative h, and then we have two subintervals. So this is going to be 2h over 2, so that is just going to be h. So h is delta x. And if we were to fill that in on our graph here, we would have two subintervals that would look like this. So these are our two subintervals right here. Okay, and we can fill this in, Simpson's rule, so that's going to be delta x over 3, and then we have times, and now we're going to name these points here. We're going to name these y values. So this is going to be y naught, all right, and this is y sub 1, and this is going to be y sub 2. So now filling in Simpson's rule, we're going to get this. We're going to have y naught plus 4 times y sub 1, and then plus y sub 2. So that is Simpson's rule for this scenario, and we have two subintervals. And really, we need to see, okay, what is Simpson's rule doing? It's going to construct a quadratic function. So it's going to construct this parabola right here. It's going to make a parabola that maybe looks something like this. And then it's going to find the area under this parabola. So in order to get Simpson's rule and talk about, okay, where does this 4, where does this 3 come from, we're going to play this out. We're going to find the area under this parabola here. And in order to do that, we're going to name this. So this parabola is going to be called g of x. And we will define g of x as a standard quadratic. So it's going to be ax squared plus bx plus c. This is just a standard quadratic function, and we're going to do what Simpson's rule is doing. We're going to find the area under g of x. So we're going to take the definite integral from negative h to h of g of x. So that's going to be ax squared plus bx plus c, and then integrating with respect to x. And now what we're going to do is integrate this and try to use some information from our graph and use some information from g of x in order to get these two things to match. Because really, this integral right here, this value is Simpson's rule with two subintervals. So we're going to get these two things to match. And feel free to pause the video if you want to try that on your own. All right, let's anti-differentiate and evaluate. So we're going to have ax cubed over 3, and then plus bx squared over 2, and then plus cx. And we're going to evaluate this at negative h and h. So we get h cubed over 3, and then we have plus b times h squared over 2 plus ch, and then we're subtracting. We have negative not x, cubed over 3, and then plus bh squared over 2, and then we have minus ch. All right, and then doing some simplification, let's see what we get. We get 2/3. Let's make that a little neater. 2/3, and this is cubed, and then these squared terms, these quadratic terms here are going to cancel, and then we are going to have plus 2 times ch. So that's what we have left over. Now, we're trying to get this to match to what we wrote out up here. So I think we should start to try to match these things. And first thing that we can try, all right, let's try to factor out an h over 3. Let's see what we get. So let's factor out h over 3. Let's take out h over 3, and we're left with what? We're going to be left with 2 times ah squared, and then plus, let's see. We take this out, this is going to be 6 times c. So that's what we have. So now we got one piece down. So let's try to fill in some other things. And again, we need to start to talk about, okay, this ah squared and c, we need to start expressing those in terms of y naughts, y sub 1s, and y sub 2s. So How do we do that? And what we can do is come back over here to a g of x. We can look at some values here. So we have negative h and 0 to play with to express y naught, y sub 1, and y sub 2. So let's look at 0. Let's look at 0. G of 0 is what? That's c. That's c. And g of 0 on our graph here is y sub 1. So we find that y sub 1 is c. So let's fill that in. Let's fill that in. That's another piece. We're getting a little closer. So this is h over 3 times 2ah squared plus 6 times c we just found to be y sub 1. So we got a y sub 1 in here. And now let's start to look at, okay, we need to start to talk about this 2ah squared term. And we need to still get some y naughts and y sub 2's in the fold. So what we can do is, again, we can start to talk about g at negative h and g at h. So let's look at both of those. Let's look at g evaluated at negative h, and we're going to get what? ah squared, and then we're going to have minus b times h, and then plus c. And then we can also look at g of h, and this is ah squared plus b times h, and then plus c. So that's what we have. And why did we do this? Remember, the g of negative h is y naught, and g of h is y sub 2. So when we add these two guys together, what do we get? We're going to have y naught plus y sub 2, and that is going to be equal to, let's see here, we're going to have 2ah squared. I like that. And then these are going to cancel, and then we're left with 2c. 2c. So we're getting pretty close. Let's just subtract over 2c. And we already know what c is, so let's do that. So y naught plus y sub 2, and then minus 2c is equal to 2ah squared. And we said c was what? C is y sub 1. So let's do that. Here we go. Y naught plus y sub 2 minus 2 times y sub 1, and that is equal to 2ah squared. And that's exactly what we needed. So let's make that substitution and see what we get. We're getting very close. So this is equal to h over 3 times, and then we said 2ah squared is all of this. So that's y naught plus y sub 2 minus 2 times y sub 1, and then plus 6 times y sub 1. And then we can further simplify. So this is h over 3 times y naught. And then we have plus 4 times y sub 1, and then plus y sub 2. And ladies and gentlemen, that is exactly what we wanted right here. This is s sub 2. This right here is exactly what we wanted, and it matches what we wrote out in the beginning part. This is exactly the same as what we wrote out up here. So you can see, all we did was play out what Simpson's rule is doing. We integrated this parabola here, and we found that this is exactly what Simpson's rule gives. Now, another note to make before we go. Say you had a larger amount of subintervals. So if we were to write out Simpson's rule with 4 subintervals, we would see something like this. We would have f of x naught plus 4 times f of x sub 1 plus 2 times f of x sub 2, and then plus 4 times f of x sub 3, and then finally plus f of x sub 4. You'd have something like this. And we showed where that 4 and that 3 comes from, but when you see this, when you see larger subintervals, you might still wonder, okay, where does that 2 come from? And if you can remember when we talked about trapezoidal sums, the same idea happens. It's because we have this double count going on. So we make this quadratic function here for these 2 subintervals, and then if we had more subintervals, this point would be shared with the next set of 2 subintervals that are making another quadratic function. So that is where this 2 comes from when we start to look at larger amounts of subintervals. It's that same double count idea from the trapezoidal sum. So hopefully this can give you some intuition behind how Simpson's rule is derived, and if you ever forget it, maybe you can come back to something like this.